Let's now see how we move from simple linear regression and individual neurons to neural networks. The basic idea is quite simple. So what we effectively do, we take those individual neurons, which is just equivalent to linear regressions, and we just stack them together. That's really it. That's a feed-forward network here, and we do it in a specific way, in a way where we organize those networks by layers. This is just something useful for the kind of computational efficiency, as otherwise we wouldn't be able to train those models. So let's just say those were kind of my input variables as I had before. This was effectively just the nodes. If we go back to before, effectively what I had here, those are kind of my inputs. And I have one neuron which kind of processes and gives me one output. So that's effectively what I'm doing right here as well. Now you have 3 inputs, and effectively each neuron now will correspond to one output here. So I have this edges here. This will effectively be a single linear regression or a single neuron. But rather than using this one, which was effectively all we did before, I can now kind of repeat this multiple times. So I can have effectively also another one. I can draw it in a different color. If it's clear, I can have those edges coming in here to get this one. This would be a second neuron. Each of them is kind of an individual linear regression there. And I can do a third one as well, where now this one again is also just a single linear regression or single neuron, and yet another one here. Now I have those 4 neurons there. So this is effectively just repeating what I did before, but saying like, rather than getting this input and sticking it into one neuron, I stick it into like 4 different neurons, and I can have as many as I like. And now comes the idea that I kind of only process layer by layer, rather than having, say, now kind of edges going all over the place. I say, well, I've set the input into one set of neurons, and now only those neurons are allowed to communicate with the next set of neurons, and only those to the next one. This is kind of introducing this layered structure here, where I have the input layer, and I have the hidden layer. In this case, it already ends with the output layer, but I could have many more hidden layers here, where now kind of those ones I just had, the output of the linear regression, are then just stuck again into another model, and so on. And if you think about the function, sticking things into each other, it's effectively like having a function, which is a function of another function, and so on. This is effectively what I have if I kind of stick those models into each other. You can see that if I draw one more line here, for example, this model here obviously is now also just a linear regression, but it takes that input rather than the raw data, the output of the previous linear regression. So effectively, it's like you could do that by hand as well in theory. I'm drawing this very non-straight. I could just say, okay, I have 3 input, 3 predictors. Let me define a linear regression. Let me define another one. Let me define 4 different linear regressions. And now I say, I take the output of those 4 linear regressions, and I kind of calculate another linear regression on top of it, which is exactly what we did here. And this is exactly what this neural network does. Kind of quite simple from this point of view. And what's quite interesting is that effectively what it allows the neural network to do is it can learn nonlinear behaviors, because each time I do this abstraction, I'm getting nonlinearities in there. But the nonlinearities are kind of coming from the fact that I'm using nonlinear functions here. If this would just be a linear function, the output would still be linear. But the thing is that here I'm using this activation function. So those things here use activations functions, like for example the sigmoid functions. Now the sigmoid function is nonlinear, and this introduces nonlinearity. I use the sigmoid as well in the logistic regression, but theirs was at the very end. When I use it at the very end, it doesn't induce a nonlinearity, but if I use it in the middle, it kind of makes the whole output nonlinear. And you can see that effectively, if you think about this pink one here, so the pink one could be like this function f. So the final output would be a function f, some kind of, say, a sigmoid function of its input, where the inputs are again functions of the original data, which could be a function of, say, this orange line here. And this is how you have this chain structured here. So I hope it's more or less clear. It's a lot of information, but think of it as multiple linear regressions stuck onto each other. So then the output would be a function of the previous function, and so on and so forth. So I'm kind of sticking those things together. So I have this chain structure if I look at it from the output backwards, basically. But if I look from the beginning, I will have this structure here. Now I've just written something quite general with two output layers, with two output neurons here. In principle, if I wanted to go back to a continuous output, I would just probably add another layer where I have just one here. But we'll see later when we talk about classification how we can actually deal with multiple neurons at the end, and how they can be used, for example, to do classification by representing different probabilities. But if I'm doing regression, my network rather should have one output there. So this is hopefully to give you some picture of how this situation, how it works. And yeah, here you have just the clean version again. As I just said, those neural networks can represent nonlinear functions. If I introduce squashing functions here, if here there are some sigmoid functions or any of the other activation functions here, then it makes those outputs be nonlinear function of the inputs. And you might ask, how nonlinear can it get? And effectively, you can prove mathematically, mathematicians can prove that if the number of neurons in this hidden layer here at the moment is 4, if I had n of them, and if I would take n to infinity, then I could approximate any continuous function. So it can be as nonlinear as you like. Any continuous function could be approximated with an infinite size neural network. Now, in reality, we will never use infinite size, but also in practice, often big size would be good enough, basically. Then we don't need infinite, just many internal neurons, and some of these more modern architectures could have millions of neurons. That's already a very big number. What people do in practice, though, rather than having one hidden layer and kind of have many neural networks, you kind of makes the model be deeper. You have more layers. That's where the name deep learning comes from, because you have sequences of layers, basically. This helps the model in the learning process. You can think of it intuitively. It's like it learns abstraction of the data. Like if you have an image and the first abstraction would be to learn some kind of edges and kind of surfaces, then the next abstraction would be to learn some form of shapes, and then the next abstraction would be to actually tell what was the object in the image there. But by using more layers, I'm enforcing somehow this way of abstraction, which helps the model to perform better. So while I'm kind of only talking about like single layer neural network, hidden layers neural networks here, and while I was just explaining that if it takes this number to be infinite, I can get any continuous function. In practice, we would use big networks, but we wouldn't necessarily use big networks which are very wide. We would rather use some which are very deep. And this is basically what I just said here at the beginning. This is just a side remark for those who like math, to see that there is actually some mathematical theory behind the whole thing. And what I mentioned earlier, like we know that training to kind of fit the model, we can do this using gradient descent, and effectively we can use the same idea of backpropagation as before. So gradient descent works exactly as for linear regression, and this backpropagation also used exactly as before. It's all I have to do is I kind of propagate all the data through, to get the output of the network. Then I compute the error using some form of loss function, obviously. And then I will basically back propagate the error and then look at the influences, and I will change the edges accordingly. Exactly what I did for linear regression in detail, only that now it works kind of in a deeper way. So the forward path is the same, effectively just going forward all the way to the end. But then in the backward path, I'm effectively kind of going step by step. I'm looking at the error, then seeing of how does it influence the layer before, and depending on how it influences, I will calculate the gradient of how much to change. And then I will basically, once this error flows through to the next layer, I will then say, okay, now I'll go back one more and calculate the errors here. So we kind of go forward, calculate the error, then I will go backward, calculate the influences, so it gets the influences here in the backward step. Then I will kind of get the kind of fraction of the error which all of those internal units contributed, and then I will take those errors and I kind of propagate them further backwards to get the influences of those edges. And like this I'm kind of going forward and then I'm going backward here. So this is the way how the forward backward propagation works. I pass forward, get the error, then I take this error, go step by step back and kind of get the influences and thus the updates there. But this step by step actually comes from the chain rule again, whereas now obviously if I have chains of functions here, if I have to calculate the derivative, I have to take like df by dA would be kind of df by dg by the whatever, and then so on by dA. Basically, I will kind of keep on calculating the chain rule, and this will actually give me kind of all those individual contributions here, all these individual updates. Now, this is a bit tricky I couldn't be possibly writing this down all by hand. This is why I have a kind of written up version of this, the equations, which I will add to the Canvas webpage. Now, it involves a lot of math and indices, so don't worry if you don't want to go through it, just kind of have a look at it. But it's really useful to kind of understand it and maybe be able to kind of work through the basics, at least to kind of see that you can understand the major steps. It becomes simpler if you look at a explicit example. The one I presented is a kind of a very generic case. But in any case, while I do not want to do the full backpropagation, I at least wanted to explain you how we can use the vectorized computations to do the different passes. For example, how could we do vectorized computations to do the forward pass? And there we just want to have a look how what kind of objects do we actually have. So we already know that the input matrix here is just this X transpose, which is of dimensions n. We already talked about that. We put the number of data points, each column a kind of different observation, and then it has like p plus 1 dimensions here, where obviously this p plus 1 would just be 3 in this case, and then I have n observations here. This is kind of the dimension of this tensor here. Are the different other vectors here, where here I have the weights and the biases. Now, those are all vectors and matrices as well. For example, before, the weights were just a vector because I had just a single neuron, which effectively just had weights like omega 0, omega 1, and so on. But now, obviously, I can have all those if they go to the J's internal neuron. So I have, say, the I's input and the J's internal neuron. So before it was just kind of 0, 1, and so on, depending on whether I had the zeros input, the first input, and then say the P's input, I would have omega P, say here. But now obviously I can have that for each of the outputs. So I have another index here, if you like. So now this omega, which was a vector before, or W, which was a vector before, now becomes a matrix here, where here I could have basically the omega 0, 0 or something like this, or 1, 1, depending on how you will define it. It's kind of the first input going to the first neuron. I could have the first input going to the second neuron. And then it's clear that because there's 3 inputs and 4 hidden layers, this thing effectively becomes a 3 by 4 matrix here. Now for the bias, I only have 1 bias each. For each of the hidden layers, I only add 1 bias. So kind of here, this is just a vector, basically 4 by 1. Now for the other weight matrix, it's exactly the same, but rather than having 3 inputs, I now have 4. And rather than having 4 outputs, I now have 2 basically. And now because there are 2 outputs, I have 2 biases as well. So this is exactly where those matrices come from. But now you can see the forward pass of the data is just some form of linear algebra computation there, where effectively kind of, let me just check, I think this one here should be, I mean how I've written it here, n times 3, that should obviously be x and not x transpose here. So obviously x has n rows and p plus 1 columns, and then kind of x transpose would have p plus 1 rows and n columns. This should be rather x. But the way how I can now multiply it out is effectively, if I now take the x vector here, which is kind of n times 3 matrix, and I multiply it by the w1, which is 3 by 4 dimensional, then obviously what I get out here is some new matrix which is effectively n times 4 dimensional. So this would be kind of the output of this intermediate layer, kind of what would be for each data point, what would be the output of the intermediate layer. There are n data points, there are 4 intermediate neurons, so this would be a kind of n by 4 dimensional matrix where for each observation I will get the intermediate output, but it's not the full output because I'm still missing the bias here. So basically what I'm doing now, once I have this matrix, I will basically add to it the bias, where I effectively say now I take what I just had and I add to it the bias, but the bias is obviously just a vector, but I'm basically rolling it out. So I will take this bias vector here and I will kind of repeat it n times to get this matrix, which is just the bias vector repeated m times. So we saw the bias vector was dimension 4 by 1 here, and I kind of repeated n times, so I'm getting this 4 by n exactly as I had here 4 by n. And now obviously the whole thing is still a 4 by n matrix, and this is exactly the output of the first layer here. Now I go further, I can take this whole matrix, kind of the output of what I just got, which was n by 4, and now I kind of again multiply it now by the second bias term, which was 4, the second weight term, which is 4 by 2 basically, for here. Oh sorry, I wrote it the wrong way around. Just to correct this. So this was obviously n by 4, and then the new one is 4 by 2, and now again I'm adding this additional term, which would just be the bias, which is now kind of 2 widths, and I'm kind of rolling it out n times. This whole thing is obviously again 2 by n. This is also n. And now I'm adding it up. So the full output here would then be n by 2 dimensional, which would just be the output of my layer, of my whole network here for all of the n observations. And this is just kind of see how we do that thing. So this would be, I take x, I multiply by w1, then I get something out, then I add to it the b1 here, then I take this output and I multiply it by w2 and I add to it b2, and then I get the final output y, if you like. So this would be all the steps, but you see what is done here is just linear algebra, and I don't have to do it one by one. I don't have to do it for the first observation, for the second observation. I can take the whole matrix of all observation, multiply it by the weight matrix here. So maybe if you color it, I will take I'm not sure whether I have so many colors. I can take this input vector here, then I multiply it by the weight vector, then I will get the input matrix. I multiply it by the weight matrix, and I get this output matrix here, which then I kind of multiply further by this. I add to it further the bias term to get the next output, and then I multiply it by the next weight term here and add to it the other bias here to then get the final output. But the thing is that rather than doing it observation by observation, I do all observation in one chunk. And this is just done by doing this matrix multiplication, as we have seen here. So the data is a matrix, the weights are a matrix, I multiply them, I get another matrix back, which is the output of the internal layer, and so on and so forth. But all I wanted to say is just linear algebra, and you can do this very efficiently. Just multiply matrices, and this is why the GPUs are so good at it, because GPUs, the graphical processing units, they are made for video games where you have to do a lot of linear algebra because you have to figure out all the perspective. This is why they are great. They were built to do linear algebra because that's what you need for games. And people figured out, well, we can actually use them to do exactly those computations. So all these matrices combined here is exactly why you need the GPUs, because here we have all this matrix multiplication. So I hope while this calculation was a bit boring, maybe the last remark makes it slightly more interesting to some of you. So if you were wondering why do we need GPUs if they're used for gaming, what does that have to do with neural networks, it's because they are very good in doing all this matrix multiplication. So the forward pass is just a bunch of matrix multiplications, but then the backward pass as well is just a bunch of matrix multiplications. And yeah, it got a bit messy there, but this was just to kind of work through the different dimensions there. I recommend you can kind of do it yourself once to kind of work through how those matrices work out. I think in the tutorials you will be building like a neural network by hand, so you have to do those multiplications, and you must make sure that you get the dimensions right, otherwise you can't multiply them. And well, to move on to training then, now we know how we do the forward and backward pass. We can calculate the kind of gradient here, and now obviously once we have the gradient we can do the gradient descent. But one thing to note is that rather than calculating the gradient for all data points as the average over all data points, I could just say, well, if I have too many data points, it just takes a long time. So rather than averaging the gradient over all data points, I could just take the gradient over a smaller batch of data points, and I just take smaller steps there. Then the gradients will be more noisy, but if I take smaller steps, I will be kind of compensating for that. So rather than computing a good gradient and moving in a large step, I can calculate more noisier gradients using batches of the data and move in smaller steps, and hopefully I will end up more or less in the same place if I do that. And this is exactly what the batch gradient descent does. So this is something I often do in practice. And what happens, obviously, if the batch is say of a size 128, and then my data is of a size 1280, obviously I will need to go through 10 batches before I have one once through the data. And this one loop over the data is called the epoch as well. And then I kind of keep on going and I iterate basically. In a sense, the normal gradient descent, each gradient is an epoch here, but here I do many steps, and once I complete the number of steps where I have once looped over the data, I have completed an epoch. And here you can see a training process where I see it runs this for 170 epochs, and I can see training and validation loss there, where effectively I can look at how am I getting better when I'm training, and I can also always look on the validation set to see how it is doing on the validation set, because here, for example, you can already see that it's kind of, the validation error is kind of flattening off, whereas training error is going down. So I'm kind of fitting to the data, so I might as well just have stopped here. And early stopping is a form of regularization as well, where I kind of keep on going, and if the validation loss is not getting smaller, then probably now I start fitting to the noise, I better get stop here. And just to mention that this optimization problem here is obviously non-convex. So now, because the function is non-linear, it's not just a nice quadratic as we had in linear regression where there's one global minimum, but it can look quite complicated, and it's quite complicated to get down there. There can be many issues. Sometimes there can be many flat regions like here, where maybe I get stuck in this region because it's so flat, I'm going tiny steps and I never get out of there. Really, I can also end up in local minima here, whereas maybe there would be a better minimum here, but I didn't end up there. So there are many issues which I would have to deal with, and this is why sometimes there are so many details involved when talking about neural networks. Now, regularization, so I just mentioned early stopping as one form of regularization, and obviously we can look at the test or the validation error, which is what was plotted here as well, and see when does it actually kind of go up again or does not go down anymore. So here you can see I can maybe stop earlier, but I can also do other forms of regularization. For example, I can do the same regularization as before. I can add the L1 and the L2 norms to the weight, and I will leave it to you to work this out, but it's effectively the same as the derivation where we introduce the regularizer. So if you go back to the linear regression calculation we did earlier, so I can obviously add the regularizer here now as an additional term, and will appear as an additional term here in the gradient, and it will take the same form as when we did regularization. And since it's kind of it's a quadratic term, and if I differentiate I will get a linear term, I will just get this extra omega here, exactly in the same way how we did the math for the ridge regression. So I invite you to kind of look at this. So if I introduce a L2 norm, I can get this additional term, and only that in the neural network literature is sometimes called weight decay. So, but this is exactly what it does. It's just an L2 regularizer on those weights basically. But you can see that if I do that, I can use the same formalism. All I have to do is add this additional term, and I still keep on doing the gradient descent. So I can do early stopping, I can do weight decay. There's one more thing which I can do, which is quite a popular one, which is called dropout. Now the idea of dropout is quite simple basically. So all I'm doing is effectively I'm taking all my edges and I'm putting like a mask over them to say, with some edges I will basically set to 1, and some edges I will set to multiply by 1, others I multiply by 0. So I'm effectively dropping some of the edges. I can say now in this step I will say drop this edge, and I will drop this edge, and I will drop this edge. So now effectively the neural network will have to kind of get along with using the other edges. So it's trying to find different relationships, similar like when we talked about bagging, you disallow it to use this one, so it has to find something else to explain the data, and this makes the model overall more robust. So it regularizes the model, and this is done randomly basically. So so each epoch I will basically apply a different mask, and then one time I drop those edges, and another time I will drop those edges, and I will do it with probability p. I will basically flipping a coin and saying this edge here, I will flip a coin and then say if it's head then I will drop it, if it's tail I'm keeping it. And obviously I can adjust this probability. I can have a coin which is biased, so it falls with probability p on head and with probability 1 minus p on tail, for example, and then I keep on just dropping those edges randomly. And what I then do during prediction time, I will obviously during prediction time I will not randomly drop anymore, but I will put each edge which is expected weight. For example, if one edge turned out to have a weight 2.0, but one time it was included, another time not, then its average weight would be kind of 2.0 times 1 plus 0 basically divided by 2, and it will just be 1 weight, which is the same as taking the weight and multiplying it by the probability a p, which would be a half in this. And this is exactly what dropout does. And as I explained, it's a form of regularization whereby by dropping edges randomly, I'm forcing the model to use alternative relationships and thus becoming more robust. And that is exactly how it works. And this is all I wanted to say about the neural networks before I now talk a little bit about implementations with TensorFlow.